Right, right on. Thank you everyone for being here and welcome to technically the day after Pi Day now, but we are gonna keep trucking along no matter the day because we need to do a full 24 hours. So my name is Alec, I'm a grad student here, and the crux of my talk today is gonna be the concept of counting. So my favorite anecdote to start out when we talk about counting before we get into the nitty-gritty is I like to pose this question. We'll pose it to the chat. I've never actually done anything with a chat before, so I'm very excited about that. What do people in the room think came first? Numbers or counting? Let's think about it for a sec. Let's say maybe Michael and I are in ancient Mesopotamia, and we're trying to figure out, how many cows we have in a field. And my question to you all would be, do we think we talked about that in terms of counting or in terms of numbers? Any takers? Yeah. Counting. Anyone think numbers came first? Numbers? One for numbers. Any more opinions? Numbers? So, yeah, numbers. Yeah, so really, there's not a great answer for this problem. I just like it because it sort of incites discussion. My humble opinion and the opinion of one of my undergraduate professors who I got the problem from said counting came first because, to tie it back to this ancient Mesopotamia, Michael and I are farming, or maybe we're, exchanging livestock. I say this because Michael is famously our resident farmer. And I ask him, hey, how many cows are in that field over there? But we don't have numbers yet. We don't have a way to say there are 3 cows in the field because 3 has not been invented yet. So instead, I go, finitely many, exactly. I would say to Michael, there are this many cows in the field, which, even though we don't have the number 3, you can tell that I'm putting indices on the cows, so to speak. I'm saying I have the amount of fingers I'm holding up is the same as the amount of cows in the field. So that's kind of the argument of you can discuss quantities without actually bringing in numbers into the equation. So that's kind of my answer to that anecdote. And we're going to be talking a lot about how we can count different quantities, different ideas throughout the next 3 hours from, what time is it? 1 a.m. to 4 a.m. What better time to talk about counting? So, looks like, and we're on counting sheep, because, famous, I count sheep at night when I can't sleep. It doesn't work. So we're going to start off with a little basic problem. We've all played Twister here. Basically, the crux of the game Twister is you flick a little pinwheel, and you have to put a certain body part, either your left or right hand or your left or right foot, onto a certain color. I believe it's red, green, yellow, or blue. So the first question being posed is, how many different outcomes are there on a twister spinner? Now, the easiest way to do this problem would be, well, I'm going to look at the spinner, and I'm going to count up the number of squares. And as you can all probably see, there's 16 there. Not that interesting. But let's think about if we say didn't have the spinner, how we would go about calculating that. And I'm actually so happy that Michael ended his talk with a discussion of trees, because in a lot of our problems to start out, we are going to be heavily discussing trees as an applied method. So I like to think about for Twister. Well, first off, I want a darker marker if possible. Let's start a fresh one. Fresh day, fresh marker. We have 4, wow, that's even worse, appendages and 4 colors. Sorry? Yeah. Is the box for dead markers? Let's go ahead. You know what? Let's try this blue here. Yep, that'll work. So we have, again, 4 appendages, 4 colors. How many different outcomes are there? Well, for each color, we have 4 different appendages to choose from. So let's say for blue, you can do either your left hand, your right hand, your left foot, or your right foot. So we can see from just this one color, we've stemmed out 4 different options. And now I'll save a little board space, but we can all see that then for each other color, there will be 4 options, which 4 plus 4 plus 4 plus 4 is going to be 16 different options. So I've talked about trees. I'm going to promise trees. If you are one of my students, you will recognize this immediately. I like to draw a little tree diagram of all the potential outcomes. So you can start by saying, well, my color is going to be either red, blue, green, or yellow. And now, of each of these options, I'm going to go ahead and stem into all the different options for the appendage in question, which I'm not going to bother writing those. But we can see how each of these line segments, each of these, what were these, be leaves, Michael? Yes, each of these leaves comes to a different scenario. So this one, for example, would be maybe red and left hand. And you can just count up all the different outcomes. We will have 16 outcomes, which the easiest way to think about all this, we have 4 options for what's going on in the first thing, so 4 different colors. And then 4 options for the next thing, 4 different appendages, which 4 times 4 is 16, which is something we would call the multiplication principle. So this is sort of a really nice small example of what we're going to be using on a much larger level with much bigger numbers and much more complex scenarios as the morning goes on, not as the night goes on, because we are done with night. So any questions on how we go about this first example? Cool? Anything from the chat? Good. Sweet. What's the next slide, I wonder? Cool. So yes, this is just sort of the theorem stated explicitly. I like to do a problem and then state the theorem, which just says we have A ways to perform a first step and B ways to perform a second step. There are A times B ways to perform the 2 steps together. So in this example, it would have been there were 4 ways to choose an appendage and then 4 ways to choose a color. So this is just sort of the theorem written out in a general stance, sort of, to get us on the proper page, I suppose. Go to the next slide, please. So yes, any Family Feud watchers? Well, there's a famous line by Steve Harvey where he says in one of his episodes, according to Steve Harvey, there's 5 suits a man needs to get: black, navy, gray, brown, and tan. You get those 5 suits, you get yourself 2 white shirts, 2 cream-colored shirts, and 2 powder blue shirts. So from all those options, how many different suit combos can we make? Well, here's how I want to approach this problem. Which also, that is, in my humble grad student opinion, just an obscene amount of suits to own in general. Even like, I feel like a suit is at least $150. That's like $1,000 minimum by the time you're done with all that. It's a bit much, but I guess if that's your job, you know? So we have 5 suits to begin with. So that's just the blazer and the pants. Then we have, I believe it's 2 black shirts, is it? Let's start. And 2 white shirts. So for each of those 5 suits with 2 white shirts, we get 2 other options there. Then for the next one, we have 2 cream-colored shirts and 2 powder blue shirts. So I hope I'm writing this correctly. We can see that for each 5 suits coupled with the 2 shirts, we have 5 different shirts, 5 different suits, 2 options for the shirt. And then, so this would we just add all these together, which we can see that each of these little tuples, 5 times 2, is going to be 10. So really, this is saying that if you buy what Steve Harvey tells you to buy, you have 10 times 10 times 10 different suit options, which is going to be 1,000. So his argument is, well, yes, you are spending a nice little sum to get the suits and the shirts. By the time you are done, you will have over 1,000 different combinations that you can do to, say, show up to work, so you can take about 3 years without showing up in the same combo twice. So certainly an investment, but it will last. Any questions on that one? No? Excellent. Cruising right along. Cool. All right, so the whole thing with a lot of these counting problems is that they do inherently invite themselves into different scenarios. This is actually a classic problem in counting. Very often it's fun to deal with change, like quarters, dimes, nickels, etc., to sort of view the different outcomes. So the question that we are having posed to us currently would be, how many different amounts of money can be made from 4 pennies, 3 nickels, and 5 quarters? So we have 4 pennies, 3 nickels, and 2 quarters, and we want to know how many different amounts of money can be made from this. So there's a very important distinction. Having this sort of collection of change invites 2 very different problems. One of them is significantly more difficult than the other. So to start out, we're going to do the easy one tonight. So the question that we're being asked is how many different amounts of money? That's not that difficult. The difficult part would be finding out what those combinations of money are. So, when I first read this problem, that was what I started solving for, and I was like, wow, this is surprisingly difficult. And then very often when you're doing a problem like this, you take a step back, you take a big breath, and you go, oh, that's not what the problem was asking. It's actually asking something much easier. So the way I would like to view this problem, I'm going to again attack it with one of our tree diagrams. Well, let's start with 4 pennies. This is going to create 4 different options for us. Then 3 nickels. Each one of these stems is going to go into 3. So this is our penny sector, I guess you could say. This is our nickel sector, or our nickel level. You can see we're kind of leveled, almost like an elevator or what have you. And then of each of these, 2 quarters. Now, I could go ahead and just count up every little stem that has fallen here, or I could apply the theorem that I learned the other slide. I almost said the other day. Anyone else feeling the time yet? Because I certainly am. And I haven't even been here the whole time. I don't know how you guys are doing it. But I can just apply my theorem and say, okay, well, if there are 4 ways to pick a penny, 3 ways to pick a nickel, 2 to pick a quarter, 4 times 3, I know that's 12, times 2, it's 24. And I would bet my lucky penny that if someone took the time to count all of these, you would get 24. 24, we're good. We are good, people. So again, just a nice little interpretation of this problem, applying the theorem and we saved ourselves the, I guess, 5 seconds that Hannah so graciously gave us just now. So, yes?
So you just counted the bottom leaves of that tree.
Yes.
Is that assuming that you have to be using one of each coin? Like, I could totally use 1 penny, no nickels and no quarters, and wouldn't that be something that isn't represented in those bottom leaves?
Ooh. Maybe. I guess in that case, we would have to count the bottom leaves and also include the first tier of leaves and the second tier of leaves. Well, actually,
We just need to add 1 to every branch.
oh yeah, 1 to every branch. Interesting.
So it'd be 5, 4, 3 instead of.
Oh, so true, exactly. So instead of, because we have to have the option of not taking 1. So absolutely. So this would actually become 5 times 4 times 3, which would give us to 60, right? Yes, 5 times 4 is 20, times 3 is 60. So yes, actually, thank you for the correction. We would have a lot more options because not taking money is always the answer. However, I would dissuade anyone from not grabbing money. Times are tough, especially for grad students. We need to pinch all the pennies we can.
60 different amounts is a lot of utility out of what? 90 points?
That is, yeah, really just the power of math. Great. Can we go to the next slide, please? All right, what are we doing next? Oh, great, Mentos. Anyone ever done the Diet Coke and Mentos thing? Yes, very fun. One of the things I learned about Diet Coke and Mentos that sort of shattered my world a little bit is that the contents, the chemical ingredients of the Mentos are inconsequential to the reaction that occurs. The reason that Mentos in Diet Coke creates such a explosion is actually because the the surface of a Mento is very, what's the word? It's coarse. There are lots of small holes in it, which are essentially a breeding ground for bubbles. So if you put an already carbonated beverage and you put a Mento into it, that is actually what creates the massive reaction. It's just the sort of space for bubbles to form.
We could create that shape and just sell it for the experiment.
Yes. However, there is a weird caveat, is that because my mom used to do that at every birthday party I had. We would always make a Diet Coke and Mentos fountain. Certain things like fruit-flavored Mentos work worse than mint Mentos, and my theory is because they're coated in more sugar, so it sort of doesn't allow the crevices to be as deep. Which, yeah, a little small chemistry lesson for free. I guess, would that be more chemistry or physics? Probably. But I digress. So, what are the facts we're dealing with here? Sorry? No, there's not more. All we know is Mentos come in a roll of 14 candies of 3 flavors. How many different rolls of Mentos are there? So, we have, in each Mentos roll, we have 14 different slots to pick, and we get to pick, do we want maybe actually I'm gonna erase that because that is no longer relevant. We get to pick, do we want maybe a mint Mento, a fruit-flavored Mento, or what other kind of Mentos are there? A what? A Memento. I like that. Directed by Christopher Nolan. Let's see, we got fruit. So each one of these slots, and we can create sort of a unique sleeve, and that's the question that's being asked. So obviously, you can be the boring person who says, I want only mint Mentos, and every single one of these slots will be mint. I guess I should have chosen a different word than memento to get a different letter in there. Spearmint. I like that.
I thought that instead of mint.
We're good. So the question at hand is, how many different ones of these combinations are there? Well, we're going to learn a formula sooner or later to tackle something like this. But for now, we can just think through it. I mean, I could literally draw out the 14 slots, but I'm not going to do that. How many options do I have for just this 14th slot? I don't care about all the other ones. I only care about what do I have for this 14th slot. 3, I see it. I agree too, we have 3. How many do we have for the 13th slot? Shocker, it's 3. So it's 3s all the way down until our last slot. So it's 3 times 3 times 3, 14 times. Well, let's think about a nicer way to represent that than this little cheeky diagram. Well, I know that multiplication, if I'm just doing 2, I can just raise that to the power. So, given that I have 14 slots, I am going to go ahead and say that I can take this 3 and raise it to the 14th power to get my answer, which is a large number. We're going to be seeing some functions this morning, I keep saying this evening, that grow rather quickly. This is a great place to start because, let's see if I actually wrote this down. This is equal to 4,782,969. Is that right?
That's what I got.
Yeah? Yes, that is how many. So, pretty big number. I think there's more on the slide. That's why my notes are off. Yes. Oh, this is the fun one. So Smarties candies come in a roll of 15 biconcave lenses, which a biconcave lens just means that it sort of creases in on both sides. Everyone here, I hope, has had a Smartie. They're like a little hockey puck that sort of push in on either side a little bit, which, you know, I don't really know the marketing reason behind that, but yeah. I'd be interested to go to a Smartie factory. Maybe that's what I'll do for spring break. But, so, exactly. Well, also kind of the opposite of a Mento, right? Because those push out. But anyway, absolutely you could, right? Mento Smartie. Well, there is the size difference, but then we'd have to convince either Mentos to go smaller or Smarties to go bigger. But
I think I prefer Mega Smarties or Mini Mentos.
yes, because also if Mentos got smaller, that would mean less surface area of crevices, which means smaller Diet Coke explosion.
Can you use more again?
That we're gonna do the math on that later. I'm sure there will be time left over, and we are gonna do the math on that. So we're just gonna apply this exact rule where instead of 3 options, we now have 5 options. Or no, we have 6 options, right? So each slot gets 6 options. And instead of 14 slots, we have 15 slots. So I'm gonna go 15, 14, 13, 12, all the way down to 1, which, using our exact same rule from the last one, we can see that this is going to be 6 to the power of 15, which is an absolutely gargantuan number. It is 470,184,984,576. That is the number of combinations you get of Smarties in a roll. And can we go to the last part of this slide, please? And now, the question is posed, 2.5 billion rolls of Smarties are produced annually. How many years is it going to take to manufacture each roll? Yes? That's a great question. We actually account for that in this formula. So what this is saying is that I can have maybe say, I have 6 different options for my pink one, or for what my color is going to be in my first slot, right? So let's say it is pink, and then maybe this is essentially creating sort of that tree diagram that we talked about earlier. 1, 2, 3, 4, 5, 6. And each of these are going to stem off. So if you were to build this tree diagram for the Smarties, first of all, I cannot think of a worse way to spend a Saturday morning. You would actually have all those strings that you talked about. I could find them in the tree for you if you wanted. So I could find the string that is pink, and then maybe white all the way down for the rest of it. So that, when I say that this is the number of combinations, both of those things that you just mentioned are included in this number, so to speak. Does that make sense? Cool.
Find the probability of those things happening, but just
Yeah, no, exactly. If you want to find the probability, it would just be 1 over this gargantuan number, which the thing that always trips me up about that, though, is that the probability of having, say, all white Smarties is the exact same as the probability of having a string of Smarties that is, say, white, pink, all the way down, which, you know, is really quite unique. But then, the last thing we have to think about for this problem is 2.5 billion rolls of Smarties are produced annually. So we take this number and we just divide it by 2.5 billion, because we're just basically saying, okay, these are the amount of distinct Smartie rolls. This is how many we can make in a year. So that's going to tell us how many years it's going to take to make all of the Smartie rolls. So doing this out, we get approximately 188 years, which I don't even know if the Smartie Corporation has been around for that long. Are we Googling? Yeah, which also I think it's important to mention that likely it's going to take much more time than this. Does anyone know why it might take way more time than this? Exactly. You're very likely to have a lot of repeats because once you've made a roll of Smarties, it's not like we're taking the same roll and making everyone share it. We're getting new ones every time.
142 years.
142 years. So they still have not made every Smartie combination, and they probably won't for the foreseeable future. I think maybe I'll contact everyone when we're all like in our 70s and be like, hey, yeah, they made all the Smarties. We're good. We can go home now. But yeah, because a repeat, once we've made a roll, a repeat is just as likely as any other, which is something we're going to see later, is how do we get rid of repeats. So, any questions on any of this?
What would it take to convince them to work with us to make these faster rather than wasting our time with repeats?
That's a good question.
Different factories making different.
Yeah. Sort of like, I feel akin to like the left Twix, right Twix scenario. You remember like when you could buy those Twixes that like, oh no, they're made in separate factories, so I can give you a bar that has 2 left Twixes in it. It's probably my favorite ad campaign of all time. Any other questions?
Is there a way to account for the repeats?
Probably not, unless you had some sort of Smartie scanning machine. I bet, well, you're a data scientist, right? Like we could probably make some sort of log of whenever we repeat, but I guess we'd have to look into how Smarties are made and like if we categorize the making of them or if they're just sort of random.
Very carefully.
Yeah. I'm just gonna, maybe we'll find the nearest convenience store and just kind of go through all their Smarties, start checking, get a data sample, do some statistics. That could be how we spend, yeah, how we spend the rest of this weekend. Yeah, let's do it. All right. QED. Was that a QED? I don't know. I have some theorems. Yes, Ambrose.
Yeah, so I mean, the closer you get to 188 years, the more likely you are to repeat having this. Like,
Exactly, right?
is there a way to figure out then, like, how long we have to go to guarantee no repeats? We're very close.
I would say no, because it's all probability. So it's like we could make every single combination of Smarties except for one, and then spend the next 100 years making only repeats. I guess I'm not a stats guy, but maybe eventually they would sort of just fall into place that we've made all of them.
Distribution.
Yeah. Yeah, we could do that.
What is it? Uniform? Or maybe like the machine systematically places them in different, like. Anyway.
Great. So, yeah, credit cards. So, credit card numbers. We're going to talk about credit card numbers. If everyone could please get out your wallets, hand me them, and I'll talk about them. But credit card numbers, I actually didn't know this before doing this problem. Credit card numbers take the form of, they have an industry ID number at the front, and every digit is obviously 1 through 9. I knew that much. Actually, I'm almost sure that they have zeros in them, but for the sake of this problem, they are 1 through 9. The issuer ID corresponds to the card issuer, and the account number is unique to the card holder, and the checksum, which is the last digit, is determined by the other digits. Given these restrictions, how many credit card numbers are possible? So just to start, the first thing I want to think about, obviously, is, well, how many numbers are there in this list that we have? How many numbers are in a credit card number? Let's see, we got, I want to say there are, so that's 10, right?
No, 69 and 1. That's 16.
Oh, whoops. 1, 2, 3, 4, 5, 6, 7. Oh, so true. Yes.
You were saying the digits are 1 through 9, but it looks like only the first digits can't be a 0. The other ones doesn't have that restriction.
Oh, you're so right. We'll take that into account right now. So the first thing, if I'm not considering anything, I would say, well, there are 10 digits, so I would just put a 10 in each slot, and I would say that the number of credit cards is 10 to the 16th. This is obviously incorrect, and we're going to basically whittle down the rest of this and see what the actual number would be. So the first thing to think about is that the issuer ID, as you just said back there, is that this is only the digits 1 through 9. So this 10 has to become a 9 because we are not starting with a 0. Next, the issuer ID corresponds to the card issuer. So that means that basically I think it's sort of, if you have Citizens Bank, if you have maybe another bank, that will be sort of the, that is specific to the bank. So that is not unique on your card. If anyone's ever bought something online, you've maybe noticed that once you start typing in the first few digits of your credit card number, it can tell you what bank your credit card belongs to. That's how it's doing that. So the first 6 numbers are not unique. Let me just make sure that's right. 1, 2, 3, 4, 5, 6. Yes, the first 6 numbers are not unique. So we can discard them because we're not dealing with how many unique numbers there are. And lastly, there's one other thing we can discard in this whole little credit card puzzle. What? Discard. We can discard the last one. We can discard the last slot because it says in the problem that it is determined by the other ones, the other numbers in your credit card, which essentially means it is not unique. It cannot be created by the other cards. Cool? Or the other numbers, excuse me. That means we only have 1, 2, 3, 4, 5, 6, 7, 8, 9 slots that are purely unique. And each of these, well, we can include 10s all the way down. So really, even though a credit card number is made out of 16 digits, we have 9 options for it, which gives us 10 to the power of 9, which is, again, a gargantuan number. I think it's in the billions, which means we don't have to worry about running out of them if everyone on Earth got a credit card. So that's a fun little anecdote on that. The 9 did not matter in the end, even though I will always make that distinction because, again, it's not unique because it's determined by the industry. You don't, even though it's 9 options, we don't even care about it. So very much in the math vein, we figured out something important that ended up being useless, but we had fun figuring it out. Okay. At this point, we've talked a lot about counting, and we're coming up on about 45 minutes, which seems like a good time to do this. Do we have any questions from the audience?
I got a question.
Michael, would you please come up here and ask your question to the audience?
Okay, so I just wonder,
folk singer Bob Dylan wrote his seminal 1964 hit. The times they are changing about the rapid social and political change that was occurring in the 1960s. What would it sound like if that song was about these accounting principles we're discussing instead?
Wow, that is a very interesting problem, Michael, that I was in no way prepared for. I reckon that it would sound something like this. Come gather round numbers wherever you roam, and admit that the ways to count you have grown, and accepted that soon your fingers and your toes are numbers too small for helping. So use your theorems and the multiplication principle, for the numbers they are changing. Come writers and students who do problems with your pens, and keep your eyes wide, we're adding it again. Don't speak too soon, for the proof has not begun. The homework is due, it's raging, and the answers elude you, for the test does begin. For the numbers, they are changing. The line it is drawn, the graph it is cast. The derivative that's slow will later be fast, as the number I add is more than the least. The function is rapidly changing, and iterate a new one to make it grow fast. For the numbers, they are changing. For the numbers, they are changing. Thank you. So that is what I reckon that would sound like. Right. No, well, actually, I think it was, so given that this is 3 hours and I only have 45 slides, I also have a few of these prepared. So I have also prepared a annoying parody count. All right, we're up to 1 so far, but it's not even 2 a.m. So, I also was just firmly watching the Bob Dylan movie before I came here. Yeah. Yeah, snubbed for that Oscar. Yeah. But alas, he soldiered on, and so shall we. All right, can we go to the next slide, please? Ah, yes. Here's another example of using this sort of principle of counting down. Those of you in my class, you will remember this. No one in here had Barrett as a TA, correct? Okay. Wherever he is, we miss him dearly, and this problem is for him. So, another way that we can approach this sort of multiplicative idea of how many options are there is through sort of one of my favorite examples, Christmas lights, because anyone who's ever hung up a colored Christmas lights knows that there are a lot of different options for what can occur. Quick aside, one of my least favorite things ever is a Christmas tree with only white lights. I find it not jolly.
Warm lights are okay.
Yeah, I think they're very pretty, like hanging in a room. I mean, I have them in my office, but I like a colorful Christmas tree. So in that vein, we're gonna figure out how colorful the Christmas tree can be. So, Barrett's circus monkey in a jumpsuit is putting Christmas lights on a string. The monkey has 9 lights, 1 red, 1 green, 1 blue, 1 yellow, 1 orange, and 4 top, which I figured out a few weeks ago is a beige-ish color. Taupe, thank you. So how many lights, how many 4-string lights are possible? So I think we can approach this problem in 2 different ways. Each bulb, we're gonna do this 2 different ways. 1, each bulb is distinct. And 2, each bulb of each color is not distinct. What do I mean by that? I mean that in this first scenario, we have maybe you have some sort of special binoculars that when you look at this 4-stringed light, if I have, say, 2 blue ones, and then I go, I'm just gonna yank these out and swap them with each other and put them back in, that maybe you have some sort of special vision where you can tell, hey, the string looks different now. Even though they are both blue lights, it looks different because you took these 2 and you swapped them. So the first way we're gonna figure it out is we're gonna assume that each bulb, that we have this sort of special vision where we can tell each individual bulb apart. Well, we have 4 lights, so let's just set out our 4 little slots. And we have 9 lights total. That means that for the first one, I have 9 options. For the second one, I have 8 options. For the third, I have 7. For the fourth, I have 6. And I want to be really clear about the difference between this problem and the Smarties problem. So in the Smarties problem, we're essentially dealing with these sort of semi-infinite sets of colored Smarties where if I put a blue one in my first part of my roll, doesn't really matter. I can put the rest as blue if I want. The difference here is I have a set number of bulbs. So it wouldn't be appropriate for me to do 9, then 9, then 9, then 9, because I put one on, I have one less to choose from. We had a case of root beer back there. You took one out, you didn't still have 6 to pick from. You had 5. So that's how we have to approach a problem like this, with a sort of limited quantity. And yes, you could argue there are finite number of Smarties in this world. We don't really have to worry about that. So we can see here that there are 9, 8, 7, and 6. And each bulb is distinct. So that's our final answer, which is going to be, let's see if I can do this in my head. I can't. 9 times 8 is 72 times 7 times 6. It's going to be 3,024. Well, now, actually, I think I might backtrack on what I said right here because we are going to get into some theorems in a little bit that will sort of go into how exactly we do this. But if each bulb color is not distinct, then what we would have to do in that scenario, essentially, is we would have to, what I call, divide out the duplicates, where let's say, just for the sake of argument, that all 4 of these were taupe. That means that sort of taupe 1, taupe 2, taupe 3, and taupe 4 visually is the exact same as the string 4, 3, 2, 1, because we can't really tell them apart. So what we would have to do in a scenario like this is essentially divide out all of these options. So I'm only going to go into this one case because the fact that we're cutting this string off makes this kind of difficult. But if they were all 4 taupe, then we would essentially take this number and divide it by how many reorderings of all 4 taupe lights there are. Which, how many orderings of them are there? Well, I have 4 taupe lights. I have 4 for the first one, 3, 2, 1. So I have 12, 24. So I would divide this out by all the 24 options where the taupe lights are distinct from each other, or that's not the right word. Yes, where all the taupe lights are moved around. So I might actually come back to this later once we've learned a little bit more, because it is quite an interesting sort of idea of how we approach this. But my students in the room and maybe on the chat, you might see that I am very much hinting towards a theorem that we've used a lot in the last few weeks of class. So yeah, sorry, we'll keep it going. Starting to feel the late night. Yep. All right. Now, we're going to talk about binary for a second. So, when I say the word binary, do people know what I mean by that? Yep, it means we compute things in only zeros and ones. Question, Michael?
No, I'm just saying it.
Yes, Michael knows binary. So, binary is, I believe, until in a few years when quantum computers become a lot more accessible, binary is what all computers work with, where basically every time you scroll on Instagram or do your homework on Canvas or anything on a screen, that is equal to your computer expresses that as a group of zeros and ones. So for example, if I was using a calculator and I was, say, adding together two numbers and I got the outcome of 5, how do I express 5 as a binary number? I believe so. I'm just going to give a quick binary lesson. Where basically we have a string where everyone is either 0 or 1. And the way we notate that is we say, well, I guess in base 10 we have the ones place, the tens place, the so on and so forth. In binary we have the 2 to the n place. What do I mean by that? I mean essentially that we take, say, basically the number 1, and we double it, and that becomes our next spot. That becomes our tens spot, if you will. And then we double it again. That becomes 4. That'll be our 4s spot, and so on and so forth. You can firmly express every natural number as a series of zeros and ones. So for example, how do I express the number 5? Well, basically you just break it down into sort of its prime factorization of 2s, where I say, well, I know that 5 is equal to 4 plus 1, and I know that 4 can be expressed as 2 squared, and 1 can be expressed as 2 to the 0th power. Which that means when I take this string of numbers, well, obviously I can only include a 0 or a 1. I put a 1 in the slots that I want to have indicated. So, well, actually, I guess it would be better notation to not even involve the last slot here. But 5 as a binary number is the string 0, 1, 0, which is 1, 0, 1. Thank you. Getting late. I was like, for a second, I was like, but the other way around, it's the same number. So, because here is basically saying, okay, well, take a 1 for the first slot, don't take anything from the second slot, take something from the third slot. And you can basically express every natural number this way. So that's a fun little quick aside about binary. Now we want to go ahead and count the number of binary strings of length 9. That's the first part of this problem. Well, let's go ahead and just make a string of 9 slots real quick. And how many options do we have for each slot? So we're sort of tying it back to what we did earlier. We have 2 options for each slot, either a 0 or a 1. So we have 2 options for each slot, and we have 9 slots. That means we're going to get to do 2 to the 9 options for how many there are, which we're not going to bother calculating that. It's not huge, but it's not tiny. And now the more fun question is, how many of these strings begin with 101? Well, I'm going to refer back to my sort of slot diagram, I guess is what I'll call this, because I'm a big fan of this. It makes it much easier to perceive what's going on. Well, let's see. I know that my string has to begin with 1, 0, 1, which if I know this slot has to be a 1, I know that there is one option for what can go there. Similarly, if this slot has to be a 0, I know that there is exactly one number that can go there. It is 0. And then same for this slot. So all these 3 slots actually are just 1s, and then the rest go back to being 2s. So even though we have a string of length 9, these 1s, because we're just going to multiply all these 2s together, and 1 times anything is 1, so that doesn't necessarily affect the amount to which we are going to be doing it. So I can say that beginning with 101, we have 2 to the 6 strings possible, which is the reason I find this interesting is because the answer to this question is the exact same as the answer to the question of how many strings of length 6 are there. So really, when you ask me, okay, fix these first 3 digits, how many more do I have to go from? Really, that's the same as just cutting off a certain amount of the string. Any questions on that? No, so that's a fun little aside of if we have to fix a certain amount of the string, you can essentially just cut it off and do whatever you're going to do with the rest of them. Cool? Next slide, please. Ready there? Okay, this is the slide I've been waiting for. So I found this tweet. Well, I found a version of this tweet like 2 years ago, and I tried to find the exact tweet, but I couldn't, so this is the new one. So, no pun intended, I love Taco Bell. It's 2 in the morning. I'm sure we're all craving some greasy takeout food. And this tweet reads, the Taco Bell menu is like, okay, we have exactly 9 ingredients. Which of these 38 ways do you want them presented to you? The reason, first of all, I have 2 problems with this tweet. The first one being, I don't like its tone. I think it's very offensive to Taco Bell. It's a great meal, especially being a vegetarian. It's one of the few spots that you can get a solid meal vegetarian from a fast food joint. My second beef with this tweet is, their math is incorrect. They are telling me that we have 9 ingredients. Which of the 38 ways do you want them presented to you? Well, let's suppose Taco Bell has 9 ingredients. No, I could not find that information on the internet. It's exactly. So we're going to assume, the problem at hand is assume Taco Bell has 9 ingredients. How many items can I make? I guess I should say, how many distinct items can I make? So in this scenario, we're going to be counting, say, a warmed tortilla as a different meal from a quesadilla. So how do I want to approach this problem? Well, as you could all probably guess, I'm going to put out 9 slots. 1 for each ingredient. So maybe this could be the lettuce slot. This could be the cheese slot. Cheese. How do you know if they're a mathematician? It's if they're a bad speller, they're probably a mathematician. Isn't that right, Michael? Yes. Michael and I share an office, and we will just shout questions to each other from time to time. Mine are all mathematical. His all tend to be spelling. That's how you know he's a very impressive mathematician. But anyway, so again, if I'm building a unique item, I'm either going to include the ingredient or not include the ingredient. So that gives me two options. I can either include the lettuce or not include the lettuce, include the cheese or not include the cheese. That means I can actually make 2 to the 9 ingredients, or I can make 2 to the 9 different meals. And I'm not actually sure what that number is, but I'm willing to bet 512. Thank you. But I'm clearly much more than 39, so they would be incorrect in stating that. So that's kind of why I wanted to bring up this. I think it's a fun example of how you could build all these different items from just 9 things. Of course, this is not accurate for a few reasons. Namely, most people don't just buy a tortilla from Taco Bell, or just technically this includes the menu item of a handful of cheese. However, right? My favorite thing that this does not account for is the fact that you can prepare the same item in different ways. For example, a burrito with cheese inside of it would be considered a different item. I know this from reading the Taco Bell menu firsthand. A burrito with cheese inside of it is different than the grilled cheese burrito, which is where you make a burrito, then you put it on a bed of cheese on the grill and you roll it in outside. So I'm not super great at pioneering the Taco Bell math department. I'm still working on getting funding for that, but we would have to sort of incorporate. So my idea is that you would have to turn, for certain items, say cheese, you would have to turn their 2 into a 3 to account for, you can either have the cheese not on it, inside of it, or melted on the outside. So really, you gotta hand it to Twitter math. Grace seems like a nice person with the fact that they were passionate enough about Taco Bell to write about it, but kind of lacking in their math. What can I say? Any questions on Taco Bell arithmetic? No.
They get a Baja Blast with cheese.
You could get a Baja Blast with cheese. Alrighty. Yeah, I would like to actually go, maybe after this, I'll go to Taco Bell and see if they would put cheese in a Baja Blast or if they would hand them to me separately and force me to do it myself.
If you get one, I'll reimburse you.
I will take you up on that. Do I have to drink it?
Yes.
Well, okay, well, then you might have lost me there. Okay, Michael, could we go for the next slide, please? Well,
One question from chat.
yes, please.
Junwei 8888.
I wonder who that could be.
He says, I'm watching this at full volume while my roommate is sleeping. AITA?
You're not the good guy, Junwei. I'm just saying I went to a very small liberal arts college with with male minority, I believe male identifying students were only about 35% of the student body. So I have not had to share a room with a roommate since I was 18. So I'm a little bit behind on my sharing roommate etiquette. But I would say listening to a math lecture talk about Taco Bell at full volume at 2 a.m, yeah, maybe you want me to ask him if we should bring him some headphones? Well, speaking of that, do you know how to pause it? I might take a short 2-minute break.
Yes, I guess. I think your mic picks it up. Say that we'll be back in a moment.
Chat, we will be back in a moment. I love it on the mic. All right, and we are back. Great. Okay, was there any topics that were prevalent? What slide are we on, by the way?
I'm still on the access.
Okay, perfect. Oh, wow, we're only at 11. We got time. Okay. Well, now, before we move on to hexadecimals, we've spent some time with binary, and I would just like to ask, do we have any questions about binary from the group?
Yes.
Michael, yes.
Stay kind of closer.
I got to what?
Okay, yes. Here's my question. Okay?
Yes.
Johnny Cash wrote the song Folsom Prison Blues in 1957, where he details the life of a prisoner in the Folsom State Penitentiary. Is there a version that imagines what it would be like to be a binary string?
That is a great question, Michael. Michael really does. I'm really impressed with his work ethic today. The question being asked again was, is there a version of Folsom Prison Blues that accounts for the what it would be like to be a binary string? Just checking. How many people know the song Folsom Prison Blues? All right, Ambrose, this is for you. I hear that zero coming, the one is around the bend, and I ain't seen another digit since I don't know when. I'm stuck with binary counting, and time keeps dragging on. But that string keeps listing on down to 2 to the K. When I was just a baby, my mama told me, son, always counting base 10, not zeros and ones. But I acted like a computer just to store my thoughts. When I see that string so long, I wish I had less spots. Well, I bet there's rich folks counting with them fancy hexadecimals. They're probably doing computations and using a decimal. I know I had it coming. I know I can't use 3. 0, 0, 1, 0, 1, 0. I imagine it would sound something like that. John Way, if you're still in the chat, apologize to your roommate for me.
Junway 8888 says, turn it up.
Anyway, so not only was that our little goodbye to binary, it was also a slight introduction to hexadecimal. So if I remember anything from my introductory to computer science course that I took in 2019, computers do not only use binary, but they use hexadecimal, which is another sort of number system that, while it's not, I remember it being not very advantageous to read as a human, it is very easy to identify as a computer. It is also much more compact than binary. What do I mean by that? Essentially, what I want to say is, if we take a look at the screen, we can see that a decimal number is much larger as a binary string. So that means it's more space that the computer has to take up, or that the number takes up in the computer's memory. So one of the ways to get around this without having to use fully decimal language is hexadecimal, where we use 16 different characters, usually 0 through 9 and A through F, but as computers are a relatively new topic, it's funny how actually, when you do think about it, computer scientists are a massive part of today's societal industry. One could have seen many t-shirts in my day that say, coders rule the world, or something along those lines. Back by like 1930s and before that, computer scientists were just mathematicians. So, tying into that, I'd also like to point out, you might say to me at some point, well, what's the usefulness of a hexadecimal if I can just use a regular decimal number? If we look here, 63, for example, takes up the exact same number of spots as its hexadecimal representation, 3F. I would say right you are for that scenario. So actually, if we play with it for a second, the number 63 has, we have 10 digits and 10 digits, which comes out to about, well, not about, exactly 100 options. So that's what the computer has to have stored in it. However, I would say, look to the number 250, which is represented by FA. Well, 250 has 3 slots, so we have to add another 10 there. And we have to turn this 100 into a 1000. But if we look at its hexadecimal representation, which would be FA, we know that it only takes up 16 in 2 slots, which if I'm not mistaken, what is 16 squared? 256, thank you. Are you doing these in your head? I'm impressed. Ah, yes. Very impressive. So we notice are you guys all computer scientists, more or less? Yes? All right. If we notice, this takes up less storage, so it is actually a more efficient method from the point of view of a computer for how to store a number. So this actually also invites some fun problems. So next slide, please. We talk about, everyone here has heard of an IP address, I hope. It's basically just you have your home address, you have maybe your dorm room's address, and your computer has the IP address, which is basically, I believe it's how anything refers to the computer. I remember there was a superhero movie I saw once. The first time I heard the words IP address was in a superhero movie where there was a starting out vigilante and some other vigilantes found him within half a day because they just tracked his IP address. So that's how important those are. Has anyone seen that movie? I'm not going to say the title of it because it has a curse word in the title, but it's a great movie.
Christian math.
Yeah, well, I don't know that. This is my first time on Twitch. I don't know the rules. I'm going to play it safe. But anyway, let's play with what this has to offer. So IPv6 is the modern protocol for identifying computers on the internet, where it's made up of 8 groups of 4 hexadecimal digits. For example, I'm not going to read that out, but you can all see it. I'm sure it looks familiar. How many possible IPv6 addresses are there? Well, I'm not even going to bother writing out all 16, or excuse me, it was 4 groups of 8?
8 groups of 4.
8 groups of 4. So we have 8 groups of 4. We could use our tree diagram, or we could just remember our theorems at this point and say, well, that leads us to 32 slots total. And we know that for each slot, we have 16 options. So I'm just going to write down, well, we have 16 for each, and we have 16, and we have 32 slots. So this is just going to be 16 to the 32nd, which for our amazing power of, I'm not going to ask you to do that, but you said you were good with powers of 2, so this got me thinking, well, this is just 2 to the 4th to the power of 32, which I guess would just be 2 to the 128th, because when it's power to the power, we multiply them. So that would be 2 to the 128th, which is a big, big number, which I would testify right here, right now, that is much larger than the amount of people on Earth. Therefore, it would sort of just follow that it is very efficient to use, and we don't have to worry about running out of IP addresses for a while. However, let's say we did. Well, first of all, we'd probably have some overpopulation problems to deal with first. But then you just add on more slots, and you're good. So I'm personally of the authority that when a number gets this big, it's easier to just represent it as an exponent instead of writing out all the digits. So if one day when I lead my own class, this will be an acceptable answer. Can we go to the next slide, please? All right, this kind of ties into these theorems that we've been talking about. I actually do want to prove one of these to finally get myself a QED down here. Oh, that reminds me. So this basically, the theorem is basically we're just going to take the rules that we've been working with this whole time and expand them a little bit. So the first theorem is that there are 2k binary strings of length k, and then expanding that to hexadecimal, there are 16 to the k strings of length k. And more generally, there are n to the k strings of a length k from an alphabet of n characters, which I thought it would be fun to prove just the first part of this, because I wasn't originally going to prove this, but then I was watching Corey's talk on induction, and it popped into my head of you could totally use induction to solve at least the first two. I'm not totally sure if you could use it to solve the third, because there are two numbers you'd have to index on, which might get a little complicated. Yes, double duct, which I don't do that. So let's go ahead and prove this claim. I claim that there are 2 to the k binary strings of length k. So, as Corey said earlier, if you're proving by induction, your first line should always be, we will now prove this via induction, because I prefer to view it as sort of a topic sentence of sorts. I was not the best English student. I would not include topic sentences. I would get points off. So when we're doing a proof, we're going to add our topic sentence. By the way, out of curiosity, how many people are on the chat right now, or just in the...
We currently have 12.
Wow. Well, I'm thoroughly impressed by that, but I'm much more impressed by the live audience. I simply do not know how you guys are doing this. I can be awake because I'm a little fired up because I'm talking through this whole thing, but if I were any one of you right now, I would be firmly asleep on my desk. So my proverbial hat's off to you. So let's start with the base case. K equals 1. Well, if k equals 1, then we would say we want to show, whoa, look at that. I forgot to write, we will prove via induction. So we want to show there are 2 to the 1, which is just 2 strings, binary strings of length 1. So we have exactly 1 slot, and we know that binary means either 0 or 1. So my first string is going to be 0. My second string is going to be 1. There are no other strings I can create of length 1 in binary. It's also simple to see how if I were doing this proof for hexadecimal, that would expand quite nicely to 16 options. So I'm going to say that this is enough to prove it for this scenario. I don't think this, what's that?
At least the base case.
Yes, the base case. This, just writing out this might not be enough in an intro to proofs class for a base case, but for almost 2:30 in the morning on the Saturday before break begins, I'm going to say it's okay. Now we get into the fun part, the inductive step. So for induction, oftentimes people say, we assume for k, we assume this holds true for k, and we show for k plus 1. I'm more of a fan of saying we assume for k minus 1, and we're going to show it works for k. Those are more or less indistinguishable from each other. Most people would accept either. I just like it because it feels good to finish on k rather than k plus 1. So we are going to assume that there are 2 to the k minus 1 binary strings of length k. Well, minus 1. So let's just draw out k minus 1 slots. We have our first slot, our second slot, up to our k minus 1 slot. And each one of them has a 2, or is a value of 2, so to speak, which sums out to, or I guess products out to 2k, excuse me, I have this, yes, 2 to the k minus 1. Well, let's take this string and let's add on one more slot to it. So I'm going to say just this is my unique string. Here, it doesn't really matter what it is. Now I'm going to add one more slot onto it. I can either put a 0 or a 1 in this slot. I'm going to put a 0 right here. Now, is this the only version of this string? I guess I should move over here. Is this the only version of this string? No, because very similar to our base case, more often than not when proving via induction, your inductive step does look quite different from your base case. However, in this, it actually looks somewhat similar. We can see that we can either put a 0 or a 1 in this last slot. So by, I'm going to say by adding a kth slot, we have doubled the number of possible strings. So, how many strings did we have? Well, we had, I'm just going to put a little arrow up here. We had 2 to the k minus 1. And I'm going to quote Michael from about 2 hours ago and say, what is math? It's turning it into symbols. So what does it mean to double the number of strings? Well, this is our number of strings. To double it, we just put a 2 next to it, which we notice this has the same base, so we can add their exponents. If I don't have an exponent written down, it should be clear that the exponent is 1. So this is equal to 2 to the k minus 1 plus 1, which is equal to 2 to the k, which is exactly what we wanted to prove. So I am done. And now I get to add my own personal tally mark to our little box down here. Pretty nice, huh? So we can see how if we were to go and prove part B, I'm going to skip that for time just because I'm going much slower than I anticipated. But also, if we wanted to prove it for part C, we would probably have to double induct, as Michael said. So could we go to the next slide, please? Oh yeah, we're going to skip this for now. All right. How many, this is a fun one. How many 20-digit strings have no 2 consecutive digits the same? So how many 20-digit strings? Well, first, let's go ahead and erase this. Any words from the chat, Michael?
Nope.
Well, at some point in this talk, I would like to get stuck on a problem or a proof so that I can say the words "chat were cooked" and mean it, because I've heard that a lot, and I've always wanted to say it for real.
You know, it's much better to get stuck and then say chat or cooking.
Well, no, if I guess I should have said "chat were cooking" while doing that, because I had fun doing that. But anyway, so
Maybe next year we can do chat.
true chat counter, and then we'll have just the John Wake chat counter as well. So how many 20-digit strings have no 2 consecutive digits the same? So I'm going to interpret this as we have a string of length 20. That's how I'm going to read this. We have 20 slots because we're also dealing with digits. So I'm going to say there are 10 digits that we could put in any slot. So, well, I'm going to say off the bat, I don't know how to solve this exact problem. So I'm going to simplify it. Whenever I don't know how to solve a problem, the first thing I do is cry. The second thing I do is make an easier version of the problem and see if I can solve that. And then if I can't solve that, I need to go get some Gatorade because I will be dehydrated from crying. What's that?
If you can't solve that, then you return to step 1. Problem you can't solve, try, then make it easier.
Then I call my undergraduate institute and ask for a refund on my bachelor's. So let's just say we're doing make a four-digit string where let's just forget the constraint for a second that no two consecutive digits would be the same. Then it would be clear that I can do 10 for each slot. I can say, okay, 10 is going to go here, 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 here. But that, of course, leaves the option of, well, 5. Maybe I have the digit 5 followed by the digit 5, which is not good. I don't want that. So the way I'm going to sort of circumnavigate that is I'm going to say, well, let's consider this first slot. I have 10 options for it. But, well, that's easy. Now for the second slot, do I still have 10 options for it? Thumbs up, thumbs down, shaking head? No, we do not. Because whatever fixed number this is, I can't have that. So my 10 options goes down to 9 options. Now, if you're like me, the first time you did this problem, you might be saying, okay, so then this goes down to 8. No, because I can have it be the same digit as the first one because they're not consecutive. So that's fine. So I still actually have 9 here, and I have 9s all the way down. Has anyone ever heard the expression turtles all the way down? Well, here I have 9s all the way down. It's funny, I heard of Turtles All the Way Down as the John Green novel. Are you holding it right now?
Not John Green. This is the Terry Pratchett.
Really? Because I knew of it as the John Green one, and then I was talking to my dad one day, and he said, you know, that's a famous saying that it's turtles all the way down.
Well, isn't it, it's also a creation myth.
Yeah, that's what. Yes, exactly. It's like what is the world sitting on? It's a turtle. Well, what's that turtle sitting on? Another turtle. Well, what happens? It's turtles all the way down, which is where that line comes from, I believe.
Did they keep getting bigger?
Well, I think the implication is, you know what, since we have time, here's the world. The pictures I've seen of this is that there are just, I'm going to try and draw my best turtle here. Oh, that's actually not bad on my part. Give him a tail, give him a little, like the best turtle I've ever drawn. And then the implication is that the next turtle down is that more or less the same size, that they're just stacked very well. But yes, apparently one day it might be turtles all the way down. But for now, it is 9s all the way down. So anyway, back to our problem. The first thing we have is that, what does our original problem say?
20-digit strings.
20-digit strings, right. So now that we're up to 20-digit strings, well, I'm just going to make 20 digits. And I'm going to say that my first option has 10 because it's sort of unrestricted by the fact that it's not in a pair with anyone else yet. And then it's going to be 9s all the way down. So if it's a 20-digit string, I would say that this would be equal to 20 times 9 to the 19th. And just to further extrapolate this into bigger cases, we would say, well, if we say we had a length string of n, and we had, well, I guess this should be a 10, my apologies, and we still have 10 digits, then the formula would just be 10 times 9 to the n minus 1, because that nth slot is taken up by a 10, and the rest all have to be 9s. And you could even extrapolate this further to saying if you have maybe a k-lettered alphabet, you would just have k times k minus 1 to the n minus 1 would be how many, excuse me, this would be how many unique words or how many words you can make that don't have 2 consecutive letters or numbers, what have you. Which, that's one of the things I do think is beautiful about math, sort of like, we've been talking about math for what, 14 hours at this point? And I do think it's important to take time to emphasize why people like us decide to dedicate our lives essentially to this subject. Sometimes it does feel like there are days where I do nothing but math. because to me, when you can take rules like this and just sort of extrapolate ideas into these crisp little formulas, there's some beauty in that that I think is really worth knowing. To me, at the end of the day, math is an art form. As absolutely corny as that sounds, it's cool enough to the point that I'm willing to do it at 2:30 in the morning on a Saturday morning.
We're rapidly approaching 5 pi hours.
Nice. So, anyway, we should be getting to one of the pretty cool long form problems shortly. Could we go to the next slide, please? And what does that say?
How many 3-digit numbers? 100.
Oh. All right, people, this is a deep problem. This is the one where I tried it for 20 minutes and then I emailed Corey to be like, how should I approach this? So we have how many 3-digit numbers from 100 to 999 is the sum of the digits even. I'm just going to write that on the board for my own sake. So this is going to be a many step process to solving this. The first thing we have to do is think about, well, which ones of these are going to be even and odd to begin with? Because as I was just talking about my passion for extrapolating ideas out of problems, we're going to do that right here. So I'm not going to write down all 3-digit numbers, but what I am going to do is I can write out all different ways that I can add up 3 digits of either even or odd. So for example, let's start with even, right? These are just my digits. They're not necessarily numbers in the grand scheme of this number. So for example, a number of this form would be 426, because each individual digit is even, but I don't really necessarily care about their sum just yet. So what I want to do is I want to write down all possible strings of even or odd 3-digit numbers. Well, how many strings are there, you may ask? We did figure this out earlier, that there are going to be, well, this alphabet, so to speak, is made up of, our alphabet is made up of the symbols E or O that I'm going to use to notate even numbers and odd numbers. So we have a 2-letter alphabet, and we're dealing with strings of 3-digit strings. Therefore, we are going to have 2 to the 3 unique strings, or 8 strings. So I've already got one of them. Let's see if we can just guess the rest. There are formulas for doing it, but I think it would be more fun to just guess them. So 1, 2. So let's even. What's another obvious one? Anyone? Odd. Exactly. Well, all right, there's 2 right there. Let's do another one that starts with even. Let's do another even again. Then this would have to be an odd. Now, let's do an even, an odd, and an odd. Wow, look at that. We're already halfway done. Did you get a good nap? Yeah. All right. Well, now we have 3. Let's do another even one. What's the only other one we haven't done that starts with an even in front of it? Even, odd, even. All right, so now we know that the rest of these are going to be odd in the front. So let's do maybe odd, even. We haven't done that one yet. Odd, even, odd. And what is the last one? Well, odd, even. Nice, right? There are formulas. We could figure this out. I was thinking about, like, when I was writing this, I was like, should we derive these where, like, you could put them each in the front? This is small enough that just some good old-fashioned teamwork makes the dream work. So now the problem becomes, which ones of these sum to even numbers? Well, I'm going to use a useful fact. I'd be happy to prove it, but we can just remember that an even plus an even is equal to an even. An odd plus an odd is equal to an even. And an even plus an odd is going to be equal to an odd. So we can use these rules to extrapolate what these sums will be. Do we want me to prove these, or are we prepared to take them on faith?
Add the QEDs.
Pad the QEDs. All right, I'll just prove that. I'll do odd plus odd is equal to even. So my claim is that odd plus odd is equal to even. Well, here's my proof. I claim that you can represent an odd number by let k be a natural number. Then the odd number is equal to 2k plus 1. Because 2k is clearly even because it's divisible by 2. So you add 1 to sort of go one ring up the ladder, and you're good. So I'm going to say my odd is equal to 2k plus 1. My first odd number and my second odd number is 2k prime plus 1, where k prime is just another integer, where I don't care if these are the same or different. It won't affect our result. So then let's just add these together. 2k plus 1 plus 2k prime plus 1. Well, let's just go ahead and add our like terms. K and k prime are not the same, so we cannot add those. So we're just going to leave them out front. 2k plus 2k prime. However, 1 and 1 sum up to 2. Now, I take a look at this new expression, 2k plus 2k prime plus 2. I can factor out a 2 out of each one of these terms, which becomes 2 times k plus k prime plus 1. Well, earlier, how did I define an even number? An even number is a number divisible by 2. Well, clearly, k and k prime are both just integers, so adding them together makes another integer, plus 1 is still an integer. So this just becomes k double prime, and thus we have this is equal to 2k double prime, where k double prime is an integer, so this takes the form of an integer, so we are good. And 2 for Alec. I kind of think it would be funny if I had the least number of QEDs, because this is very much a problem-solving section where you can sort of get the vibe of the theorems, and you don't really have to prove the theorems. But anyway, so let's use this rule, these rules here, to calculate what these sums will be. Well, an even plus an even plus an even is going to be even. An odd plus an odd plus an odd, well, 2 of these odds come together to form an even, but then we add an odd to it, it's going to stay odd. This is going to be odd. Then we have 2 evens, which add together become an even, plus an odd is going to stay odd. An even plus 2 odds is going to be even. 2 evens plus an odd is going to be odd. This is going to be even. Even again. Is this one right? Yes, because this becomes an odd, odd plus, yes. And lastly, odd. So now I know what all these different cases, if you will. A big thing in math is proof by cases. We know what all these different cases are going to be. So now I can just get rid of the odd ones, because the question is asking how many sums add up to an even number. Well, so we can say we're going to get rid of options 2, 3, 5, and 8. So there are 4 different sums that add up to even numbers. I'm just going to rewrite them down here. We have our first one is even, even, even. Our second one is even, odd, odd. Our third one is odd, odd, even. And our fourth one is even, odd, even, odd. What I like about this is that these clearly respect the rules that we set out here that we've already proven, that basically if you're going to get an even number, it either has to be all 3 evens or 2 odds and an even, which we can see here. So let's go ahead and count. Let's just start out with even, even, even. Well, how many even numbers? Remember, we're going from 100 to 999. So thinking about the first digit, as far as I'm concerned, can be 2, 4, 6, or 8. That gives me 4 slots. And you know what? Same for these other two. So that gives me 16 times 4, which is going to be 32, 64 options. Is my math good on that? You stole the second half of my proof, but you've been very helpful, so I forgive you. But yes, let's go over that. So this is going to give me 64 options. This next option, well, we have, again, 4. And then, wait, 2, 4, 6, 8. Wait a sec. Oh, these can be 5s, excuse me. These can be 5s because they could be, say, 208 or 200. We're counting 0 as an even number here, which I'm not a number theorist. I'm not going to state outright that 0 is an even number. But in this scenario, it will hold for that. So there we have 455, which is going to be 100, actually. Pardon my mistake. Again, 4 here, and then 5 for either one of these, because we have 1, 3, 5, 7, 9. 5 options. Which again is going to be 100. Now, and I believe this is what you might avoid. This is what you're talking about? Yes, this is what you were talking about. We have 3 here. We have, well, because this is an odd number, again, we have 1, 3, 5, 7, 9, which is all good. 5 options, 5 options. And then here for this last one, we are again going to have 5 options, correct? Comes out to 125. And this last one is going to be, again, it will be 555 because we have 5 odds that could start it because, well, 0 is not being considered an odd number, so we're all good there. Then we have 5 evens, and then 5 more odds. And lastly, now that we have all these, we're just going to sum them together, and we're good. 125, 125, 250 plus another 200 is going to give us 450 different unique how are we saying this again? 3-digit numbers whose digits sum to an even number. Very nice. Very nicely done. Yes. QED. I don't know if that's a QED, man. That was a problem, not a proof.
Feels like QED to me.
Maybe I'm going to say, and thus it is so.
I'm gonna do the Alec classic. Thus, therefore.
No, it's fix,
So, thus, therefore.
fix, thus, so, therefore. Michael asserted a few weeks ago that you can make any proof out of fix, thus, so, therefore. Okay, let's see. We're coming up on about 2 hours. Let me just see what the next one is. Oh yes, permutations and factorials, because I do have a very fun math problem coming up that involves the guitar. It's not a song this time. It's actually, I'm going to do some music theory for you all, but we do have a few more concepts to learn first. So, permutations and factorials. Hit it, Mr. Bruner. All right. First one, this was a problem I borrowed from somebody else. Goku Ball, Dragon Balls, that's from Dragon Ball Z, correct? Yes, I don't know. I've never played that or watched it, whatever. But the structure still raises a fun little question of this person has 7 Goku balls, or how many orders can Dragon Balls, and this person, Goku, wants to know how many ways can they order them. Well, I'm not going to spend too much time harping on this. We have 7 balls for the first slot. 6, 5, 4, 3, 2, 1. We're going to discover that there's a very nice name for this structure here of multiplying by counting down from a number.
I think you need to put a tally in the here there be dragons.
Who put that up? Whose idea was that? I love that. Can we go to the next slide, please? Okay, so next, how many hex strings of length 10 are there without repeated characters of like 16, of like 17? I'm not going to harp too much on these, but we can all see that it would be 10 times 9 times 8 times 7 or 16. Basically, you just start at the number it asks for and then you multiply down until you get to 1. Does everyone get what I mean by multiply down? It's not very good verbal notation, but I think we understand what I mean. The reason I'm sort of being ambiguous about my wording here is because we're about to come to a very nice wording for all of this. Next slide, please. Yeah, we can skip this. All right, so what we call this is factorial, where basically we say that n factorial is defined as n times n minus 1 times n minus 2 all the way down to 1. So, for example, 4 factorial is equal to 4 times 3 times 2 times 1. And then we would say the only thing we have to really categorize about this is an incredibly useful tool that shows up a lot in probability and counting and all sorts of stuff. And the only major thing is that clearly 1 factorial is equal to 1. And I'm not sure the theory behind this, but for convenience and for elegance, we say that 0 factorial is equal to 1. I don't fully understand the theory behind that. It's just sort of a designated rule that we have. And I think, we're approaching 3 p.m. Any questions from the group? 3 a.m. God. Michael has a question. Oh, we have another question, a real question first. Please.
Is 1 factorial also 1?
Yes, because so 0 factorial, while it doesn't necessarily follow the rule, we define it that way. We just say this is the rule for all numbers that are not 0. This is the rule for 0. So because 1 is a number that is not 0, we just say 1 factorial is equal to 1 times whatever numbers are behind it, which is just 1. So yes. Any other real questions before we go into a bit? Yes. You could take the negative of a factorial. Well, I guess negative factorial would kind of, let's play with that for a second. I guess if we're doing like -5, well, it would have to be this sort of absolute 0 because we define factorial as all the way to 1, which in that case, though, you'd have to pass 0, which would just negate everything. Yeah.
Well, I mean, what if we just tried to multiply, instead of multiplying down, what if we just tried to multiply up? So it should be -5 times -4 times -3 times -2 times -1.
Which also would be positive or negative depending on if you started at an even or odd integer. So you could do that. Yeah, you could define that.
Interesting.
Yes.
Chad also has a question.
Yes.
Will you later explain the algorithm to determine the strong connected components in a diagram?
No.
Okay. I have a question.
Yes, Michael has a question.
In 2009, the Plain White T's broke through to the mainstream with their song, Hey There, Delilah. The song details someone being enthralled with a woman named Delilah. But I kind of was wondering what it would be like or what it would sound like if our narrator was instead infatuated with factorials.
That is a great question, Michael. You're just rocking away with these tonight. Rocking. So the question, just to restate it, is what would it sound like if Hey There, Delilah was actually about factorials instead of a woman named Delilah? I'm going to move this over here. And I imagine it would sound something like this. Hey there, factorial, what's it like growing so quickly? I am just a constant function, but much slower than linearity, yes I am. Times tables can't grow as fast as you. I know it's true. Hey there, factorial, how do you multiply by n minus 1? I'm doing this math by hand, I'll use Mathematica when I am done. Check to my answers, to my surprise. 0 to you is nice. Oh, it's how you grow so fast. 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 1000x seems pretty big, but you've got 999 times 998 times 97 times 96. Exponential makes fun of us and we'll just laugh along because we know that we will never grow that fast or be in the choose function at last. Oh, it's how you grow so fast. Oh, it's how you grow so fast. Thank you. So that is what I expect would be from that perspective.
There's a comment in the chat.
Yes.
The song should be on Spotify.
That's. I'm more of a fan of Pydora, but you know. Wait, what? What?
It must be 3 a.m.
God.
iTunes during the olden days.
PyTunes and. Or what? I prefer Pinal Records. This is getting too much. Anyways, let's go ahead. What slide is this?
21. Factorial to whatever this is.
Okay, we are. You know what? I might do some other stuff first. So let's do. We're on slide 21 right now. 22. Okay, we'll go ahead and skip this. I'm planning on because I do have some long form problems I wanted to get to and one more song. These were too much fun to write. Okay. We can skip that as well. All right. And yeah, isn't this the same as the other one? Yes, one more ahead, please. So sorry. Oh, sweet, we're at the problem I wanted to be at. Okay, so this is actually, I am gonna use the guitar in a non-comedic fashion for a moment to explain how we can use this math in music theory, actually. So, any musicians in the room? Yeah? So, the problem, I'm just gonna go ahead and read the problem. Could you change that back for half a second? Thank you. In music theory, there are 7 traditional modes. These are called the Ionian, Dorian, Phrygian, Lydian, Mixolydian, Aeolian, and Locrian. Using only, well, yes, they're real, right? Other musicians? Yeah. Well, another name for the Ionian scale is the major scale. And I believe, what is it? Aeolian is minor. Those are the other ones that have names. But I'm going to show you how using only these rules, we can actually derive all 7 of these modes. So a mode is 7 notes, and between each note is an interval. So for example, I'm just going to play in what we call the key of the people for a second, which is C major. A C major scale is made up of 7 notes. And you'll notice that wants to resolve back to C. So that is C, D, E, F, G, A, B, which is the scale. And then we go back to C, which I'm playing C, excuse me. These are both C notes. We consider them, in the context of this problem, we consider them the exact same note. If there are any pianists in the room, you know that they are not the same note. You call them by certain octaves. Actually, just a quick aside, this note that I'm playing right here is referred to as A4, I believe, and it is generated by, or we call it A4, by the fact that when I pluck this string, what is happening is this string is moving back and forth at a rate of 440 times per second. So you can't see it because it's moving so fast and also because you're quite far away from it, but that is actually what generates a musical note, is just vibrations. There's a joke that if you don't have your tuner on you, that if you just clap 440 times in a second, you can use that note to tune. A lot easier said than done. So,
Mathematician's solution to the problem.
Exactly. They're absolutely useless and absolutely correct. So, that is how you know someone's a mathematician. So essentially here, we are just going to say that these two are the same notes, and there have to be 7 of them. And each interval, when I say an interval, that means the space between 2 notes. So for example, is an interval. And every interval is made up of either a semitone or a whole tone. A semitone, it's nicely shown here on frets of a guitar or any fretted string instrument, is just when you go from one fret to the next fret. You can hear it barely changes, but it does change. If you have a piano, which you can't really do it on the guitar, well, I guess you kind of can, that if you play 2 notes that are 1 semitone apart from each other at the same time, it does not sound very good, which is because the frequencies mess with each other, but that's not really the math we're dealing with today, though that would be fun to talk about at a later time. Anyways, all we need to know for this is that a semitone is 1 step, a whole tone is 2 steps. So you can hear the difference between and. So from there, we can think about, we know that each interval between subsequent notes is either a semitone or a whole tone. And all intervals in one cycle of a mode add up to 12 semitones. That means that even though I'm doing a combination of semitones and whole tones when I do, that all the whole tones I'm doing, because they count as 2 semitones, this is going to add up to 12 semitones total. And the last major rule is that semitones must be cyclically at least 2 steps apart. That means, so when I'm doing my scale, I'm never doing 2 semitones next to each other. I can do 2 whole tones next to each other, which just sounds like, it sounds fine. But 2 semitones next to each other doesn't fit into a traditional mode. That's just something we have, is that you don't really do that. That's actually very commonly found in the blues. I'll do a quick aside where there's actually this thing that's very common in blues where you would play the 4th, the flat 5th, and then the 5th. So you could do like, which gives it sort of that bluesy feel. This is called the tritone, which actually, fun fact, was illegal in medieval times. You were not allowed to play the tritone in a piece of music because it was thought of as the sound of the devil, which then you get into modern music, it's very revered in certain circles, yada, yada, yada. But I digress. That is just a rule we are given. So the last thing I want to talk about before I put down the guitar is that when I say different modes, actually, I am going to put down the guitar and I'm going to talk about how we derive them first. Let's put that like that. Okay, so we know that we need to have 7 intervals, right? We need 7 notes, but we also need 7 intervals. So, and we know that these intervals can either be written as a 1 for a semitone or a 2 for a whole tone. Yes? So, we also know that these 1s and 2s need to add up to 12. Well, let's think about all the ways we can do that. I'm saying all the ways now as sort of a little foreshadowing, if you will. So, I'm a simple guy. Let's start with the simple scenario of all 1s. Which any 5th grader could tell you, all these 1s added together does not equal 12. It equals 7. So that's clearly less than what I want. So what can I do? I can turn one of these into a 2. And that will up me by 1 to 8, but still not good enough. So I turn another one into a 2. I get a 9. I'm going to keep doing this until you recognize that 5 of these have to be written as 2s. It should be noted that at this moment, even though they're technically in a line, I don't care about order just yet. So 5 of these 2s are all next to each other, and this is going to add up to 12 because 2, 4, 6, 8, 10, 11, 12. there is no other combination of 7 2s and 1s that add up to 12. That's not really worth proving. You can just kind of take a moment to convince yourself of that, right? Because if I change any one of these 2s to a 1, I've gone too little. I change any one of these 1s to a 2, I've gone too big. So I've already figured out a good chunk of this, that I could have, I can have 5, so I need 5 whole tones and 2 semitones. So, for example, I could actually literally do this order. I could do whole tone, whole tone, whole tone, whole tone, whole tone, half tone, semitone, semitone. However, what's wrong with this order that I have up here? Yes, it breaks rule number 2. It breaks that rule that says, okay, I can't have 2 semitones next to each other. In fact, even if I took this 2 and this 1 and I swapped them, that still wouldn't be good enough, because my rule specifically states all intervals in one cycle, or excuse me, all semitones must be cyclically 2 steps apart. So first of all, let's figure out, if I don't care about order, how many options do I have for putting these together? If I don't care about my second rule, how many options do I have? Well, I have 7 intervals total, and I can put any one of them in any spot. So that means I have 7 factorial to begin with. However, now we have to address something obvious, or excuse me, something not obvious, because it wasn't obvious to me the first time I did it. If I just do 7 factorial, to me, that's distinguishing between whole tone, and whole tone. It's treating each tone as its own distinct thing, which we do not want to do. So again, just for sort of simplicity's sake, this implies that whole tone, I'll label them 2 and 1 is not equal to whole tone 1 followed by whole tone 2, which clearly it is, right? It's an interval, so they're the same exact thing as each other, so we don't care which order they come in. So that means we have to divide out all the ways that we could reorder the 5 whole tones and the 2 semitones. So we know that we have 7 factorial, but we also know that there are 5 whole tones that we don't care which way we swap them. So we divide by all the ways there are to We divide by all the ways there are to move around all the whole tones with each other, which 5 whole tones, how many ways are there to reorder them? 5 factorial ways. So I'm going to divide by 5 factorial. However, that is not good enough because I also have my 2 semitones, which if I swap their order, it doesn't change anything from a musical standpoint. So I have to divide by 2 as well, 2 factorial, excuse me, which is also an important distinction. The factorial has to go inside the parentheses because otherwise it would just mess up everything in the denominator. So, funny enough, if let's say this was like a homework problem to calculate this without a calculator, here's a sort of a fun way to do that. I'm going to leave my 2 factorial alone in the front because I don't want to deal with that right now. But I'm going to write out 7 factorial. Well, that's 7 times 6 times. And now I'm also going to write out my 5 factorial in the denominator. Well, I know that if I'm only doing multiplying and I have a fraction, that I can divide stuff in the denominator and that's common in, I can cancel out stuff that's in both the numerator and the denominator. So these 5s go bye-bye, these 4s, these 3s, these 2s, these 1s, and I'm left with 7 times 6 over 2 factorial, which 2 factorial is just 2, because it's 2 times 1. So we can even rewrite this as 42 over 2, which is going to equal 21. So as of right now, I've done nothing but applied rules 1 and 2. I haven't even touched the third rule yet, and I've whittled this down to 21 different possible modes. And this is letting two whole tone semitones be next to each other. So now let's think about how we can get rid of all those. And also, this is one of those problems where you have the answer given to you in the problem statement, and your goal is to get to that answer. You're not like searching for it, because I mean, if you weren't doing this work carefully, you could just stop here and say we're done. But I can go, no, I don't have my answer yet. I know what the answer is. I need to find it. So I'm just going to rewrite my 7 steps, and I'm going to think about what happened. So as of right now, remember, I'm saying that I have 21 different things that could occur. However, I know that these 2 slots are not allowed to both be semitones. I also know that these 2 slots cannot be semitones, or these, or these, or these, or these. So that leaves me with 6 different things I can automatically take away, right? Because those are essentially permutations that are not allowed. However, there's one word that's really important in Rule 3. All semitones must be cyclically at least 2 steps apart. Because, well, if you think about a scale technically goes on forever. I'm not totally sure about the physics behind that. But once you do all the intervals, what do? You do all the intervals again and again and again, which means technically once I finish here, I just loop back around here. So the last thing I have to remove is these 2. The beginning and end cannot both be semitones, because then they would be cyclically next to each other, which violates Rule 3. So I have 21 minus 6 minus 1 more. Now notice I have 14 modes. So just by eliminating all the options where the 2 are right next to each other, I'm down to 14 modes. Now I'm going to pay extra special attention to that Rule 3, and I can say that they must be at least 2 steps apart. So I've done 0 steps apart. Now I can look at 1 step apart. Well, let me clean up this board for a second. Sure is dark out. Do people like how's everyone's biological clock? Like, do you feel like it's 3 a.m.? Yeah, this ain't good. Yeah, I mean, I'm on that little Red Bull parade right now.
I'm feeling like 9 a.m.
Yeah, but like, I mean, I was on the phone with my big sister, who is a nurse who works like 7 to 7 shifts at night. And she told me, she was like, don't drink more than 1 Red Bull. You're going to regret it if you drink more than 1 Red Bull. And I kind of want to drink more than 1 Red Bull. But I kind of see where she was coming from now. But anyway, now let's go ahead and get rid of, well, here's one combo that's not allowed, right? The first and the third. Here's another. Here's another. So we have 1, 2, 3, 4, 5. I can get rid of 5 right there, right? So I'm down to here. Then, remember, I can take my second to last slot and my first slot. That is a combination that is not allowed, because I go 1 step, I go another step. There's technically only 1 whole tone between them, which is not allowed. So I can get rid of that one. And then last, but certainly not least, if I'm on the last interval, then my first one has to be empty. So that's 1 more I can get rid of right there. So 1, 2, 3, 4, 5, 6, and then 7. This is, this is an interval that's not allowed. Being on the last and the second, not good enough. So I can get rid of that last one. So I can say that now we are down to our 7 modes, which here's a little Easter egg for everyone. So we can see through just some basic combinatorics, we've determined that given these rules, there can only be 7 modes, which let's write down one of the modes. It can be whole step, half step. I should be saying whole tone and semitone. When I say whole step and half step, it kind of depends on the type of musician you're talking to. These are interchangeable terms. So, I should say, I'll say whole step, half step, whole step, half step. Let's make sure these don't violate anything. Well, I've got 5 whole steps and 2 half steps, so we're good. And I've also got a group of 3 between the 2 half steps and a group of 2 between the 2 half steps, so we're good there. Now, here's something that I think is just pure beauty when it comes to the intersection of music and mathematics. This is clearly an appropriate permutation. And when I start here and I end here, cyclically, end the relative term. However, if I start here and end here, this is a different mode. That actually, we have this sort of cycle that generates all 7 modes. I said earlier, we were looking for 7 modes. We have 7 notes. We have 7 intervals, excuse me. So, depending on which interval you start on, we actually generate a new mode. So all 7 modes are are just different cycles of the same path, essentially. And let me show you from an auditory standpoint how beautiful that is. So, my favorite key to play in is the key of the people, the key of C, which, because if you're playing on a piano, that means you only touch the white keys. So I'm going to touch only the metaphorical white keys on my guitar. Now, everyone, I'm going to play this maybe 2 or 3 times, and I want everyone to think about what this scale sounds like to you. What emotion does it invoke? It's just a scale, so it won't make you really feel the emotion, but it might invoke a feeling. Let's see if I can do 2 octaves of it. Would anyone like to share? Yes. That might be because of external factors, but I really appreciate them. Well, I would say it's a happy sounding scale.
When you were playing just the 1 scale, I felt kind of high, and then when you did 2 of them, I was more of a cow.
True. Now, let me do something a little funny. So this is actually what I'm playing right here. I'm starting on this whole step here, and I'm doing whole step, half step, whole step, half step. Now, I'm going to permute this a little bit. I'm going to play it in a different order. And I want you to tell me, does it sound like a vaguely different emotion? Wait. It sounds wrong, that's why. To me, and it could be difficult because I'm not playing it in context, I'm not playing it with a band behind me, what have you. Well, even I could just play versus these are the exact same notes. However, they have different feels to them because I'm starting at different parts of this cycle. So what I'm doing right now is I'm playing, this is the, I believe this is the Ionian mode, which is the major scale. And then there's also the, I believe it's the Aeolian mode, which is the minor scale. Which most people argue sounds significantly sadder than the other. Which I think the only thing that's causing that is starting from a different interval. Which I genuinely, again, not to be corny, It's 3 in the morning and I've been doing math. I'm going to be a little corny. I think there is some real beauty and mystery in the fact that just based off of where you start in a permutation, you could argue that that affects one's emotions. Yes?
So have we mathematically proven that you really can get off on the wrong foot? If you take a half step instead of a whole step, you can just ruin your whole day?
I would absolutely argue you can. If I listen to a song in the key of C major on my bus ride to work, I will be significantly happier than listening to a song in the key of A minor. What's the difference between those two songs? Intervals. Just where I start on the intervals.
Follow-up question.
Mm-hmm.
Can we QED this proof?
I think we could QED that. I'm going to QED that. I will happily fight anyone who says we cannot QED that. I think Professor Mark Kale would stand with me on that because he was the one who gave me the idea for this problem. Yes.
So to like prove you wrong, what if I chose to word happy after listening to an A minor song?
I'd say we have to consult some external factors. Yes. Yeah, it's okay. I'm just moving back and forth. It's been on time for like 20 minutes. Let's see, if I duck, yeah, the camera. Yes. Anyways, that's sort of my long little music theory talk. Nana, just a heads up, I expect about another 20 minutes out of me, if that's cool. I don't want more. I'm exhausted.
I feel great.
Yeah. Which, all the power to Nana, she has not left the building since 9 a.m. today.
Yeah, I got here at like 8 days.
Okay, but anyways, let's get into we're in the almost the home stretch of this. Wow, it's funny, I've been counting 3-hour intervals all day today because I've watched all my colleagues do this. It feels much longer when you're watching someone else do it than when you're actually doing it. Also, I'm going to go ahead and add one more to the annoying unnecessary parody count, which those are largely for me more than anyone else. There is one more in store, by the way. What?
Are those separate?
Oh, which one? Oh no, there's one on the there's two here because I couldn't see it. Then there's one over here, and then there's one more over here. But writing these is one thing, memorizing them for the bit is another. Yes. Which, I mean, I've done worse for the bit, but you know. Aha. All right, let's read this next problem. A baseball team roster often has 13 position players, non-pitchers, who are available to bat in a given time in a given game. A lineup is an ordered list of 9 positions that start a game. How many possible lineups can be made from 13 players? Well, let's just go through it, right? Now, one of the key things to emphasize in this problem is that you don't repeat players in a baseball game. So we have 9 players. It's getting late, man. You could tell me a 3 is a 5 right now, and I'd believe you. You could tell me an epsilon is a 3.
We already
Yeah, we know. We were losing it. Okay, so we have 9 slots here. Obviously, I cannot do 13 because if a player goes once, they're done. There's no crying in baseball. There's also no repeating in baseball. I say that like I've played baseball before. Here's a quick aside because it's funny. My parents were able to tell very quickly that I was not one for like team sports because they signed me up for soccer against my will, and I spent more time running through the mud than I did chasing the ball. Like everyone was on the other side of the field chasing the ball, and I was just doing laps through the mud pit. And my parents were like, maybe we should get him in something else. But I digress. So we have 13, 12, 11, 10, 9, 7, 6, 5, which basically we can see that this is just almost 13 factorial. But what do we need to do? Well, we need to get rid of 4 factorial, 3 factorial, or excuse me, 4, 3, 2, and 1, which the way we deal with that is we put something factorial underneath. Well, I know that I have 13 players and only 9 slots. So that means the sort of bottom 4 slots are forgotten, which we can denote as 13 minus 9. So this actually ties into a formula that, excuse me, the Red Bull really does, it gives you wings, but it kind of hurts your tummy too. Yeah, I'm like jittering. And I had a pot of coffee before I came here too. Yeah. But then, so we have 13 factorial over 13 minus 9. I want everyone to notice that 9 was the amount of slots we have. So this would actually be, this is actually a known formula in counting, which we call, it's not choose, because that's something different. Permutation, yes. This is, we would denote it 13p3, which is just saying, I have 13 people and 9 slots. How many options do I have here? Which sort of ties into the rest of this problem. So I'm not gonna calculate that. It's getting too late for plugging that into a calculator. Yes.
Yeah, what is this, a 3, 4?
That should be a 9. I'm losing it. I apologize, everyone. Some of you have been here since 9 a.m. I genuinely do not know how you've been doing it. I am severely impressed by you all. So a baseball, let's see, we have a lineup, how many possible people? Well, and again, to just figure out a baseball season lasts 162 games. You take this number and you divide it by 162. That gets you how many seasons it will take. We're not going to bother with the rest of it because we are severely behind. Yes.
I would like to point out that for this problem, you said we're in the home stretch.
Mm-hmm. Let me emphasize. Oh wait, the puns. The puns are real. I was about to say I'm more in my mental home stretch in that my brain will cease working in about 25 minutes. Yeah. So that's that. Could we go to the next slide, please? And could I see it up on the monitor?
Yeah.
I wish it was. There we go. Yes. So this is exactly it. A permutation is an arrangement of a collection of objects into a particular order. In other words, a string where each object appears exactly once. Really, guys, we've been working with these since 1 a.m., which I've kind of the way I wanted to arrange this talk was sort of dealing with ideas before giving you the definitions, because I do think that to a certain extent, just sitting down and getting a bunch of definitions thrown at you can be very intimidating, and I think it's more fun to sort of unearth them and then be given, hey, this actually has a name. Like to reference guitar again, a lot of guitar players learn the chords and then figure out that they have names to them. So I believe that's called inquiry-based learning. Yes, we have a very good math ed department here. There's a lot of inquiry-based learning. And there are n factorial permutations of n objects. One thing that's always helped me is that I like to think of a permutation as a podium. Or a list, but I think a podium is more fun. So for example, how many ways could you put 3 people on a podium? 3 factorial ways, because I can make 3 lists where person 1 is on top, person 2 is on the second, person 3 is on the third. So, which this just kind of has a nice form to it. I think in a few slides I'll emphasize the sort of podium idea a bit more, because also we do deal with, this is a permutation, there's also combinations, which is where we don't really care about the order that the people are in. So say like, I could ask everyone in this room to form a line, or I could all just observe you all sitting here as a group. I don't care who's first or who's last. That's kind of the difference between a combination and a permutation, which for me at least takes a few times hearing it to fully understand it, but we'll get into that a little bit later. All right, next slide, please. So this is a fun fact. there are exactly 52 factorial ways to shuffle a deck of cards, which is just 52 times 51, which you can, all the way down, which you can sort of rationalize to yourself as saying, you can think of the top card, or you can take a deck of cards, put one down. There were 52 options you had to put that one down. Then the next one you had 51 options, which actually ties into an interesting fact. Kind of ties into the Smarties that we were talking about earlier, actually, which is if you shuffle a deck of cards, if you take any deck of cards, I know Professor Darnell, Rick downstairs has a bunch of them in his office. You take one, you shuffle it, it is highly likely that that order of cards has never existed before in human history. That is how large 52 factorial is. It is, I would argue, a number that is so big that I don't even bother trying to perceive it as a number to myself. I believe there is some evidence about what humans can comprehend in terms of large quantities. But yeah, I believe you can fact check me on that. If you shuffle a deck of cards, there's a good chance that order has never been made before. So again, you think about, like, yes?
It's 8.07 times 10 to the 67.
Right. Be a 10 followed by 67 zeros. That is absurd, isn't it? And if you just think about, like, in the time that I've been talking to you, in Vegas alone, there have probably been hundreds of decks of cards shuffled at this very minute, because as we all know, Vegas never sleeps. Exactly. Right? There's a movie about mathematicians who go to Vegas to try and count cards and stuff goes awry. No, they do it. Yeah, you're right. Well, don't they get into legal trouble? I watched the first 10 minutes and it wasn't a very good movie, so I stopped watching it.
There was the door problem, right?
Yeah. My favorite thing about that movie is that they're in like a normal calculus class and the professor like singles out a student for being like, Newton stole calculus from Leibniz, which is a hysterically simplified version of what happened, which is like, he's just like super just like pushy, like, yeah, Newton stole it. Like, he's not a genius, which I don't know. I find humor in that, but also it's just a real thing that happened that then they made a bad movie on. All right, can we go to the next slide, please? I think we have some fun problems to work with. Yes. Oh, there we go. 80 unvigintillion. I don't even know what language you derive that from. Well, let's do how many permutations of 1, 2, 3, 4, 5, 6, 7, 8, 9 are there? Well, there's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 permutations, which is kind of funny. Let's see. We're gonna skip some stuff. Yeah, let's go ahead and skip the rest of this slide. Definitely over-prepared. Oh, this is a fun one. A group contains n dogs and n cats. How many ways are there to arrange these animals in a row such that the dogs and cats alternate? So, I like the good luck, especially because, well, my dog, he's very much a dog. He doesn't sit still when a cat is around. So trying to line them up would be a tall order. Michael, you're a cat guy. Do you think you could even get your cats lined up in a line?
It's just, you gotta put the little tuna dishes out in the line and the cats will grow themselves.
True. Yeah. Well, let's think about what this would look like. This would look like, well, we would either have dog, cat all the way down, or what's the other thing we could have all the way down? Cat, dog. I was about to say I should have put a picture of cat, dog, which growing up, you don't really think about that until you're older, that cat, dog is a very bizarre looking specimen. But anyway, so we have two different things. Let's calculate either of them. Well, for my first dog, I have n choices. For my first cat, I have n choices. For my second dog, I have n minus 1 choices. For my second cat, I have n minus 1 choices. all the way down to one choice times one choice. Now, you guys know what I love about multiplication? It's commutative. You can reorder it. I could technically make this. This is the same. This is equivalent to n times n minus 1 all the way down to 1 times n times n minus 1 all the way down to 1, which is equivalent to n factorial times n factorial, which, if we're just trying to compress this expression as much as we can, is n factorial squared. Again, it is very important to put the parentheses and the exclamation point in the proper spots because n factorial squared is absolutely not n squared factorial. These are two different things. I don't even want to think about what n squared factorial is. But, so we know that one of these orders is going to be, I'll just say it's cat dog, is n factorial squared. And we know that the other one follows the exact same diagram. So they are both of these orderings are n factorial squared. So combining them, our answer is just going to be 2n factorial squared, which is a large number depending on what n you pick. Cool? That would just be putting a dog and cat in front of each other. Just be like, yeah, that'd be like cat dog, but separated. Which I'm sure there has been an episode in that series where they like get magically separated. Did anyone watch like Dragon Tales growing up? Yeah. Do you remember there were those two dragons that were like conjoined? Yeah, and there was an episode where they get separated like magically, and then they discover that they like being conjoined. Yeah, which I think there's kind of
Dragon Tally.
Oh yeah! I might not be doing much in the QED department, but I am killing it in the dragon department. No.
But I guess you can join.
Forgot when I was.
Well, no, I think conjoined things are still count as two different entities. Like, there's all this research too of like if you're conjoined on the brain, is it one brain or two brains? I believe the consensus is it's two brains. But I am off topic, but it's fine. It's almost 4 a.m. Yeah. I actually woke up at 2:30 last night, 24 hours ago, and was like, wow, I'll be teaching at this time. That is nutty. All right, but I think, and then yes. So I'll just go into this last definition, but the number of ways to select k objects without repetition from a set of n things is denoted, and this is, we say out loud, n choose k, even though it's a little, it's like n on top of k. What's that?
You've done like half of my slides already.
I'm sorry.
It's okay.
Half the slides. Yeah. You want me to just, I'll just start over. Do the same slides again and again. And then this, we call this n choose k. Oh yeah, and this is also important that it's without repetition. And it reads as n choose k, and it's called a binomial coefficient. So actually, we used this earlier in the musical mode problem. I just didn't want to let everyone know that actually n choose k is equal to n factorial over n minus k factorial. Is there one other bit in this equation? Yeah, that's right, times k factorial, which just gets rid of the copies essentially, because n choose k is a permutation. It is not a combination, which means that order does matter here. Wait, order doesn't matter, excuse me. It is getting late, I'm getting sloppy. It's so late, it's early.
It's getting less. It's getting late.
Yeah. How long have, can't believe we've been at this for almost 19 hours. Yeah. Has anyone been just observing the whole time?
We got that crazy guy right there.
Yeah. You deserve like a medal or something. I went home and took a nap. Like, wow. All right.
You're the crazy guy we're talking about.
Yes.
You've been here since now.
Yes. May I ask you, sir, what made you decide to stay here the whole time?
Him.
How so? And you're saying that on a live stream. Well, I apologize for Michael's actions, but we're very happy to have you here. Don't want to admit fault. Okay, let's keep on trucking. I think I've got about 5 minutes left in me. Sorry, Nana. All right, keep going, Michael. I'm gonna find one more good problem to do. Keep going. One more. Okay, go back. Let's do, yeah, we're gonna do the Fisher random chess problem and then we're gonna end it. All right. I'm very happy to be opening for Nana on the first night of tour.
The Oilers.
Your Oilers tour.
1989.
2025. God, does anyone ever just realize that we're in the year 2025 and it kind of freaks you out a little bit? Yeah. What about the calendar? Alrighty. So, let's go ahead and read off the problem. We have in Fisher random chess, which I have never heard of before this problem. My girlfriend and I have started playing chess at one of the coffee shops in town, and it's made me realize that I'm really bad at chess. I'm very impulsive and I don't think things through. And if you do both those things in chess, it shows very quickly. Because it turns out chess is mostly just thinking things through. Anyway, in Fisher, what's, but like with chess, it's like, I don't know why. It's very different to me.
You know, you can make a mistake, crumple up your piece of paper, throw it on the ground, and start over. People get real mad if you do that with a chess match.
Yeah, I crumpled up the coffee shop's board I was asked to not return. Okay, anyway, Fisher random chess, the starting pieces on the back rank are randomly arranged subject to the following rules. The two bishops must start on both colors, one black, one white. The king must be placed on a square between the two rooks. How many starting positions are there? Well, let's just go ahead and draw the back line of a chessboard. Well, the front line is just pawns, right? Oh, I thought back line refers to the back part of either player's setup, I think.
Are the setup symmetric, or can I have a different setup than you have?
I don't know about in Fisher random chess, but in normal chess, it's symmetric except for the king and queen. So, and I'm just going to draw them, do black or blue, I guess, in this hip new wave chessboard I've got going on. So, the bishops must start on the two colors. So, well, I can see here that for one of my bishops, I've got 1, 2, 3, 4 options. For the other bishop, I have 4 options. So, for just the bishops, I have got 4 options for one, 4 for the other. So just off the bat, I have 16 options just by placing down my bishops. Everyone cool with that? Yes. So the next part we have to figure out is for the the putting down the rooks with the king in between them. Well, I have, let's just say I knock off these 2 slots. Then I have 6 slots left, and I have to decide where to put 3 pieces, essentially. So even though the king has to be between the rooks, that doesn't totally matter, weirdly enough. And I'm not going to be able to explain this beautifully because I'm kind of getting a little exhausted. But we have our new binomial formula. We can actually apply that here because we have 6 spots and 3 pieces. Therefore, we have 6 choose 3 is going to be the number of ways that we can arrange our 2 rooks with a king in between. because we have, well, 6 for the first. Well, let's just do out the equation. So funny enough, the denominator looks like that because 6 minus 3 is equal to 3. So following the equation we had earlier, we get to, it just looks the same. So we can knock out these 3 right here. And we're left with 6 times 5 times 4 over 3 times 2 times 1, which just sort of neatly puts our 3 pieces in any 3 spots. And because we're doing the choose function, we are dealing with combinations, not permutations, which allows us to put the king in the middle nicely. I apologize, I can't explain that as well as I wish I could right now. The hour is getting to me, but nevertheless, we move forward. So for then the king/rooks, we have 6 choose 3, which I believe that is 20 ways. And then, so that gets rid of 3 more pieces. And then we have 3 last pieces, and we don't care where the items go, so we just do 3 times 2 times 1. So for the last ones, we have 3 factorial, which is equal to 6. So now all that's left is to multiply these items together, and we get 16 times 20 times 6, which is equal to 1,920 different ways to put on our back row in Fisher Random Chess. Alrighty, so I do have one final little tune for you all, and then I will be heading out. I will be sitting down to watch Nana as long as I can before I fall asleep. And I'm very weak.
Next week.
I digress. So, thank you all for your attention during this time. I had a good time. I'm very tired. And I wanted to write one more parody song about being a mathematician. So this is, I'd called this House of the Math Department instead of House of the Rising Sun. There is a house in Missoula they call the math department, and it's been the ruin of many a poor boy and me. I know I'm one. My mother was a professor. She taught the kids chemistry. My advisor was a pure math man down in UMT town. Now the only thing a mathematician needs is a whiteboard and an expo marker. And the only time that he's satisfied is when it's QED. Oh, mother, tell your children to go past calculus, to spend your life using sine and cosine in the house of the math department. In the house of the math department. Good night, Missoula. Okay, thank you all very much for your attention. Live stream to Nana Myers is up.
Like, put us on a break.
Yeah, how do you do that?